So, what actually happens when artificial intelligence just stops waiting for our instructions? Think about it. Every single day, we fire off literally billions of prompts to AI models. Billions. But despite that staggering volume, the relationship is still, well, kind of static. We ask a question, it gives us an answer. It's basically a game of tennis. But what happens when the AI starts holding the racket, serving the ball, and then literally sprinting over to the other side of the court to return its own serve? What happens when AI moves beyond just sitting there waiting for our prompts and actually begins acting, evaluating its own results, and improving entirely on its own? Welcome to The Explainer. Today, we're unpacking a really fascinating transition that's happening right now in the tech world. We're looking at the architect's guide to loop engineering. And the core premise we're exploring today is that AI is, well, for lack of a better term, it's growing up. It's shifting from being this static tool that needs constant handholding to a dynamic, autonomous system that can actually operate independently. Understanding how this mechanical shift works is absolutely vital for grasping the future of technology and ultimately figuring out your place in it. Okay, let's dive right into this. We're going to start by moving beyond simple prompts. Then we'll break down the anatomy of the loop, compare prompts versus loops, check out some real-world applications, weigh the benefits and challenges, and finally, look at the future of autonomy. Section 1. Beyond simple prompts, moving past static AI. To really get where we're going, we first have to recognize the limitations of where we are right now. Traditional AI just kind of sits there, totally idle on a server, until a human being gives it a very specific instruction, right? It doesn't initiate, it doesn't reflect, it just reacts. And that brings us to this incredibly important definition: loop engineering. It's the process of designing AI systems that autonomously act, evaluate their own results, and then improve themselves through continuous feedback cycles. You'll definitely want to commit this concept to memory. Instead of a machine waiting for you to hit the enter key, imagine an AI tasked with researching a market trend. It pulls data, realizes half the links are dead, and without asking you what to do next, it automatically rewrites its own search query, finds updated sources, and compiles the report. We're engineering systems that teach machines how to learn from their own attempts over and over again, completely unprompted. Section 2. Anatomy of the loop, how AI improves itself. So let's look under the hood and see how these self-improving systems are actually built mechanically. This right here is the core feedback cycle. It kicks off with an input, say a goal or a specific data point. Next up is the action, where the AI actually attempts the task. But here is where the absolute magic happens. Step 3, evaluation. The AI looks at what it just did and measures it against the desired outcome. Then comes step 4, improvement. It adjusts its own internal parameters or approach based on that evaluation. And finally, step 5, it repeats the cycle. Think of it less like a basic calculator and way more like an autonomous manager. Let's say you ask this AI manager to compile a massive research report. In step 2, it writes a draft. In step 3, it evaluates that draft, fact-checks itself, and realizes, oops, I just hallucinated a stat about global supply chains. A traditional static AI would just hand you that hallucinated stat. But this autonomous manager catches the error, fixes its process in step 4, and runs the draft again. It's a completely self-contained loop of improvement. Now, to make that cycle work reliably, we need a few specific components in place. We need clear goal definition, so the AI actually knows what success looks like, task execution, result evaluation, and robust feedback collection. But what's really interesting here is the concept of human oversight. Because as autonomous as these systems are designed to be, human oversight remains an absolutely critical, indispensable piece of the puzzle. We are the ones setting the guardrails. We have to make sure the AI doesn't just spiral off into unintended directions or get stuck looping infinitely on a misunderstood goal. Section 3. Prompts versus loops, a shift in capability. It's incredibly helpful to contrast this new paradigm directly against what we already know and use every single day. And this breakdown brilliantly illustrates the exact difference. Prompt engineering is kind of like hitting a brick wall. It's a one-time instruction yielding a static response in a single interaction. Think of it like giving very literal, step-by-step instructions to a super fast but highly literal intern. If your instructions are flawed, the intern builds a flawed product, hits that brick wall, and just sits there waiting for you to fix it. Loop engineering, on the other hand, actually finds a way through that wall. It represents continuous improvement, adaptive behavior, and multi-step workflows. It's like hiring that self-correcting manager we talked about. If they hit a roadblock, they don't just stop and wait. They adapt, reroute, find a workaround, and keep pushing toward the broader goal without needing you to hold their hand. It is a massive, game-changing shift in capability. Section 4. real-world applications. Loops in action today. Let's move on and see how this actually builds into active deployments that are happening right now. The sheer cross-industry breadth of loop engineering is honestly staggering. We're seeing this power autonomous AI agents that can browse the web and execute complex multi-step tasks for you. We're seeing it in autonomous coding assistants, customer support bots, recommendation systems, and self-improving business workflows. But honestly, maybe the most fascinating application is in physical robotics and automation. Right now, robotics companies are using loop engineering to teach humanoid robots how to walk in digital simulations. The AI makes an attempt, falls over, evaluates exactly why it lost its balance, adjusts its gait, and tries again, thousands of times a second. By the time that software actually touches a real physical floor, the robot already knows how to walk. These aren't sci-fi concepts for 10 years from now. They are literally here today. To make this even more concrete, let's look at these real examples. Think back to our input, action, evaluate cycle. When an autonomous coding assistant writes a piece of software, it doesn't just present the raw code to the human developer. It actually attempts to run the code itself in a secure sandbox. When it inevitably encounters an error, what does it do? It doesn't give up and wait for you. No way. It evaluates the error log, rewrites the code to fix the bug, and runs it again. Or take a customer support chatbot. It answers a user's question, gauges their satisfaction based on their follow-up questions, and refines its conversational approach in real time to provide a much better answer on the very next try. The AI is literally learning in the wild. Section 5. Benefits and challenges. Weighing the risks. Because, look, with this incredible autonomous power comes a very real set of cascading risks that we absolutely have to balance. On the benefits side, it's amazing. We get better accuracy, massively reduced human intervention, continuous learning, and improved decision-making. It's a total dream for efficiency. But the challenges? They are equally steep. For instance, if the feedback quality is poor, the system learns the completely wrong lessons, which directly leads to error propagation. From a purely mechanical standpoint, if an autonomous system can improve a workflow at lightning speed, it can also amplify an error or reinforce a data bias at that exact same speed. An AI left to loop without proper safety and governance can rapidly optimize for the wrong things entirely. And we can't ignore the computational costs either. When an AI gets stuck in a loop, endlessly trying to solve an impossible problem or chasing a flawed goal, it burns through massive amounts of server power. Letting an AI run continuous loops in the background isn't free, and we have to weigh these realities really carefully. Section 6. The future of autonomy. Where is this taking us? So, the absolutely crucial point here is this. Loop engineering isn't just some passing trend or a neat little niche programming trick. It is the foundational architecture shaping the future of autonomous, self-improving AI. It's the very blueprint for how systems will soon operate, adapt, and evolve entirely on their own. We're building the infrastructure for machines that don't just compute, but actually comprehend their own mistakes and actively strive to overcome them. And understanding this today gives you a massive advantage. Whether you're managing a team, building a business, or just trying to stay relevant in your career, knowing that we are moving from static tools to autonomous partners completely changes how you should be planning for tomorrow. And that leaves us with a fascinating and maybe slightly uncomfortable question to ponder. As we engineer these systems to evaluate their own work, fix their own errors, and continuously improve without us, when AI learns to loop perfectly, what will your role be? Will you be the one setting the goals, the one providing the crucial human oversight, or will you let the loop run entirely on its own? It is definitely something we all need to be thinking about right now. Thank you so much for joining me for this explainer. Keep learning, keep questioning, and I'll see you next time.